Hello student, in this video we will study ICSE 10th grade first chapter of the physics force. So the topic which we are going to cover is translational and rotational motion, moment of force or torque, couple, equilibrium of body, principle of moment, center of gravity and uniform circular motion. So before we start the topic, first we will see the introduction of this chapter. In ninth grade physics, you studied about the Newton's second law. So from Newton's second law, we derived a formula force is equal to mass into acceleration. We derived the formula F is equal to m into A. By applying Newton's second law, we know that F is equal to m v minus u divided by t. And v minus u by t is equal to acceleration. This formula, we got it when the body is the uniform acceleration. So if you substitute the value here, we will get m into A. So force is equal to mass into acceleration. So when we apply the acceleration, then the position of the body will change. Means if the body is at rest and we apply the acceleration, so force will act on the body and force is responsible for the motion in it. Force is a vector quantity. It means that it has a direction. It could be positive or it could be negative. Generally, on the right side, we are considering force as positive, and left side, we are considering force as negative. And the SI unit of the force is Newton. So these all things we studied in the ninth grade ICSE chapter. Now we'll start our topic, which is type of motion. Hello student, Anand Academy providing CBSE and ICSE board classes from 6th to 12th grade, and we are taking maths, physics and chemistry classes. Mode is both online and offline. Our center is now in Bangalore, so if you want to know more, you can visit anand.academy or you can call on this number. So first is translational or linear motion. What is the meaning of translational or linear motion? You can see this example. Here we have a box, and this box is initially at rest. So when we apply the force, then what will happen? The box starts moving. And this motion is in a straight line or a straight path. So when we apply the force and the body starts moving in a straight line, then it is called as a translational or linear motion. Similarly, for the rotational motion, as you see the example here, here is a circular body and this is a fixed part. So fixed part, what will happen? If you apply the force, the body will not change the position. Means the body remain at rest and the body will not change its fixed position. But when we apply the force, as you see here, we are applying the force. So what we will notice, the body starts rotating. So when the rotation takes place in the body without change in the position, then that motion is said to be a rotational motion. So I'm explaining one more example where I took the condition of both translational and the rotational motion. Let's see this example here. In this, we took the circular body, and this is the point A of a circular body which is touching the surface. So when we apply the force F, so we will notice that the body starts rolling. Means the position of the body will also change. As you see, initially the body was at this position. Now after that, body reaches to the different position. And parallelly, body also starts rotating. The point A, as you noticed, initially it was touching the surface. After a certain time, it will reach at this position. And then again, it will come to the initial position. So here you can say that both rotational and translational motion takes place. So what is the definition of a translational motion? Translational motion is the motion in which all points of the moving body move uniformly in the same line or direction. Example, a train moving on the track. Like this is the track of the train and here the train is moving. So train is moving where? A straight path. So it is a translational motion. A man walking on the road. This is second example. Both are translational motion. Many examples are there. So we can take any of it. Next is the definition of rotational motion. Rotational motion is the motion that occurs when the body rotates on its own axis. Means position is not changing, but it will rotate on the fixed axis. Like the door. When we open or close the door is not moving anywhere. Door is fixed, but it starts rotating on the axis. So that is the example for the door. Same way, blade of the helicopter. When helicopter blade rotating, so axis is fixed, but it will rotate on the axis. Even our at home fans are there. This is also the example of rotational motion. Now we will study about the moment of force or torque. Moment of force or torque. This is responsible for the rotational motion. Means if moment of force is present, it must be the rotational motion. So how it is possible, we will understand now. As you see in this figure, this is the fixed point or it is a pivoted point. It says that the body is not changing the position. Body position is fixed. And here we are applying the force on this body. So that's why AP is the line of action because in that direction the force is acting. And OP and AP both are perpendicular to each other. It means that the length of the OP, which I represent it as R, it is always perpendicular to the line of action. So when we are applying the force, so what we will notice, the body starts rotating because body can't change the position, it's fixed. So this force will helpful to rotate the body. So moment of force is a relation between force and the perpendicular distance. So we can define moment of force as the product of the magnitude of the force applied to the distance of the line of action of the force from the axis of rotation. So in formula we can say that moment of force is equal to force into perpendicular distance of force from point O. So F is equal to R into F. So in the magnitude form, F into R sine theta we can say. So it means that this moment of force depends upon the magnitude of the force, which is F, and the perpendicular distance R. As you see in this figure, we are applying the force F in this direction and this is the R. So if our force is equal to 0, it means that moment of force will be 0. So moment of force, we represent it as tau, it will be 0. Why? Because it is equal to F into R. So if F is 0, then the total moment will be 0. Second, let's assume that force has a magnitude, but R is 0. R is 0 means now the force is acting in this direction. This is the force here. So R is 0 means R lies on the axis. So in this case also moment of force is 0. So these are the two conditions where the moment of force could be 0 when force is 0 or when perpendicular distance is 0. We will understand this concept by using one more example. As you see in this figure, we have a door and this is the handle of the door. Here is a person wants to open the door. So when the person applied the force F and this distance is R. So when R value increases, then F value has to decrease. So that's why the door handles are always present at the corner. Means it is always at the farthest distance from the axis. This is the axis, these are the hinge. So force should be less. If this handle moves towards the axis, suppose here, then you have to apply more force. Force value will increase. Because see, if we have to close or open the door, moment of force has a fixed value. So if this moment of force has a fixed value and you are changing the R value, so F value will also change. Let's take an example. If I consider moment of force, which is tau, is equal to 100 Newton meter. So tau is equal to F into R. If it is 100 and we are applying 50 Newton of force, so R must be 2 meter. This is the case 1. Second case, you can assume I am applying 20 Newton of force. So in this case, R will be 5 meter. So as you notice here, when I am increasing the value of the R, force value decreases. So in this case, the person will apply lesser force. But when the handle is moving towards the axis, so force must increase. And on the axis, force will be 0 because R is 0. So that's why if you apply the force on the hinge, door will never open because moment of force is 0 and moment of force is responsible for rotation. So now we can say that factors affecting the turning of a body is the magnitude of the force applied and second the distance of the line of action of the force from the axis of rotation. So moment of force is responsible for the turning effect. Force is not responsible. Force is taking part, but as you noticed when we applying the force on the hinge where R is 0, so body will not rotate. So it means that force is affecting the turning effect, but force is not responsible for turning effect. Moment of force is responsible. But for linear motion, force is responsible. When we apply the force, then only the body changes its position. I hope this part is completely clear because many times a student has a confusion in this topic. Now we will see the unit of moment of force. So we know that moment of force is equal to force into perpendicular distance of the force. So force unit is Newton and perpendicular distance means meter, which is the SI unit of the distance. So the SI unit for the moment of force will be Newton meter. In short, we write it as Nm. In ninth grade physics, we know one conversion, how to convert Newton to the kgf. kgf is also the unit in term of gravitational force. So 1 kgf is equal to 9.8 Newton. So in term of gravitational unit, Newton meter can be converted to the kgf meter. According to question, we can use this. Now the CGS unit. We know that 1 Newton is equal to the 10 to the power 5 dyne and dyne is the CGS unit of the force and centimeter is the CGS unit of meter. So if we convert it, 1 Newton meter is equal to 10 to the power 7 dyne centimeter. How it is 10 to the power 7? 1 Newton is equal to 10 to the power 5 dyne and 1 meter is equal to 100 centimeter. So total is 10 to the power 7 dyne centimeter. If you are facing any problem, you can also comment me. So I will try to clear your doubts. These are the conversions that we can remember. 1 kgf into meter is equal to 9.8 Newton meter and 1 gf into centimeter is 980 dyne centimeter. This we are using to solve the problem. As the force is a vector quantity, so here moment of force is also a vector quantity. It means that it has both magnitude as well as direction. So for moment of force sign convention, anti-clockwise we are considering it as a positive charge and clockwise we are considering it as a negative charge. It means that if we have a body here and this body is moving anti-clockwise direction. So we are considering it as a positive, means moment of force is positive. And if we consider same body but it is rotating clockwise, then we consider it as a negative. So this is used when we are solving the problem. With the help of one rule, we can also identify when the moment of force is clockwise or when it is anti-clockwise. So for this rule, take a right hand and keep it in the thumb upward direction and rest forefinger in the horizontal direction. And just try to close all the four fingers. So you will notice that when it is a anti-clockwise rotation, that time thumb is upward direction. And when it is a clockwise direction, the thumb is in the downward direction. So that's why the direction of anti-clockwise movement in this case is upward, and the direction of clockwise direction is the thumb will be inward. So upward is considered as positive and inward is considered as negative. When we are solving moment of force concept, that time we definitely focus on this sign convention. I will explain you few questions for better understanding. Now we will see some example of moment of force. First is a wrench used to loosen a nut. As you see in this figure, here is the nut and we are using the wrench here. This is the wrench. And you see the person applies the force at the maximum distance from the nut. Because when the distance is maximum, then the force will be minimum. Because R value will increase. So that's why if we have to loosen a nut, we always apply the force at the corner. Let's see other example. Turning of a two-ten wheel of a bicycle. Here you see this is the bicycle, wheel is there, and when we apply the force in this direction, so the wheel starts rotating. And because it is connected to the chain, so when the wheel is rotating, driver wheel is rotating, then the driven wheel will also starts rotating, and both are rotating in the same direction. Both are rotating clockwise direction. So this is another example of moment of force. As you see here, this paddle is more in the length. So in this case, it's easier to rotate the wheel. So we apply the less force to rotate the wheel. If the paddle is shortened, then we need to apply more force. Next example is, this is the jack screw which is used to lift the car. Car is a heavy, so we can't lift it easily. So that's why we are using the jack screw. And here this is the rod we are using to lift this jack screw. So you see in this figure, the person is applying the force at the maximum distance. So by applying the less force, the jack will lift the car easily. So these are the few example of moment of force. Now we'll start our second topic, which is couple. So couple is applied when two parallel forces of same magnitude but applies in the opposite direction and do not share the line of action. This phenomenon is called as coupling. As you see in this figure, we are taking a rod and this is O is the fixed point of the rod. And at the both the corner A and B, I am applying the force of same magnitude F. But both the force are applied in the opposite direction. From O to A, it is applied upward. From O to B, it is applied downward. So when this type of condition is present, then it is said to be the couple. And this phenomenon is called as coupling. So why we are using this couple? So see, when we have to open any container, we are using the both fingers to rotate it. Because if you try to use one finger, then the container will not open. So this couple will makes our life easier. I will explain you with some example. As you see in this figure, turning a tap water. This is a tap water. And when we have to open the tap, we are applying the force in both the direction and the magnitude of the force is same. So then after that the tap starts rotating. But if we try to apply the force only one direction, then we have to apply huge amount of force and might be possible that we can't open the tap. Second example, tightening the cap of the ink pot. This is the ink pot here. If we have to tightening the cap, we apply the force in one direction and another force in the other direction, and then we start rotating. So by this method, we can easily tighten the cap of an ink pot. Next example is turning a steering wheel. So we are applying the force in one end in upward direction, second end in the downward direction. But always remember one thing, both the forces will follow the same sense of rotation. Same sense of rotation means, as you see, this force is acting upward, but it goes in this way. So it is a clockwise. Similarly, if I apply the force in this way, so it is also going clockwise. So both are using same sense of rotation. So here in this example, this force is rotating in this direction. So it is a clockwise. Same way, this force also rotating clockwise. So when we are applying the couple concept, we always rotate in the same direction. I hope this part is fine. Let's derive the formula of a moment of force. So we are taking the same example that we discussed previously. Here the same force F applied in the opposite direction, and this is A and B, two ends of the rod, and O is the pivoted point. So if we have to find the moment of force at OA, so we can say that it is equal to F into d by 2. So this d by 2 means this distance is considered as d by 2 because total distance is d. So half of it is d by 2. Similarly, moment of force for OB is equal to F into d by 2. This part is also d by 2. So as I told you, clockwise direction is considered as negative and anti-clockwise is considered as positive. So in this case, it is following clockwise, so it is negative, and this is also following clockwise, so this is also negative. So we can put the minus sign here. So net moment of force is how much, or net torque is equal to how much? Minus F into d by 2 minus F into d by 2. So we can consider it as minus F into d. So for formula point of view, we are not putting minus because it could be clockwise or it could be anti-clockwise. This is the example of clockwise, so that's why it is minus. But it could be possible that the force is in the anti-clockwise direction. So that's why we simply write it is equal to F into D. Means couple is equal to force into total distance of the arm, which is AB. So same thing, here it is mentioned, moment of force at end A is F into OA and the moment of force at end B is F into OB. So total moment of force is F into OA plus F into OB. So F we can take common, OA plus OB is equal to total distance AB. So moment of force formula is F into D. So this is the formula. Now we'll start our third topic, which is equilibrium of a body. So equilibrium is only possible when no net force is acting on the body or no net moment of force is acting on the body. If I explain you in a simple language, as you see here, if we apply the force F, then the position of the body will change. Means after a certain time, body will reach to this position. It means that the body is not at equilibrium. When we can convert to the equilibrium? When we apply the same force but in the opposite direction, so net force is here 0. Then we can say that body is at the equilibrium in term of translational body or translational motion. See, if we have a circular body and this is fixed and we are applying the force here. So when we apply the force, the body starts rotating, but the position of the body is not changing. It means that translational motion is not present here, but rotational motion is present. So that's why when any body has to be completely in the equilibrium form, it must be possible when the net force is 0. So it means that no translational motion. And when the net moment of force is 0, then it is no rotational motion. So for complete equilibrium, both translational and rotational motion should be stopped. So when it is possible, for translational, net force should be 0 and for rotational, net moment of force should be 0. So we can define the equilibrium of a body when a number of force acting on a body produces no change in the state of rest or of linear or rotational motion, then the body is said to be a state of equilibrium. So for translational or linear motion, the condition is total force should be 0 or the resultant of all the forces should be 0. And for the rotational motion, the algebraic sum of moment of all the forces acting on the body about the point of rotation should be 0. It means that total moment of force should be 0. Then it is a rotational equilibrium. Now we will study about the type of equilibrium. So there are two types of equilibrium. One is the static equilibrium and second is the dynamic equilibrium. So always remember, whether it is a static or dynamic, the condition of the equilibrium should be satisfied. Means if it is a static or dynamic, in both the cases, net force and net torque should be 0. This is the condition. But what is a static and dynamic equilibrium? I will explain you. So we know that there are two types of position of a body. A body could be at rest or uniform motion. So these are the two types of the position of the body. So when we consider the body at rest and then the equilibrium takes place, it is said to be a static equilibrium. But when we consider the body is in the uniform motion and then we consider the equilibrium state, then it is a dynamic equilibrium. Like you see, if we put the notebook on the table and the body or the book is at rest, so that time it is a static equilibrium. Means the body or the book is not changing the position because no external force is acting on the body. Second, it is not rotating because no net moment of force is acting on the body. So this type of equilibrium is the static equilibrium. What is dynamic equilibrium? Suppose in a space, we know that it is in a space it's a vacuum and we throw the stone in the space. So the stone will move with a uniform motion because there is no external force acting in that environment. So in that case, net force is 0 and the moment of force is also 0. But it is a case of dynamic equilibrium because we are taking the body in the uniform motion. So here already the definitions are also mentioned. When no external force or the moment of force is applied on the body will be in the state of rest or uniform motion. So what is the definition of the static equilibrium? When a body remains in the state of rest under the influence of several forces. Like example, I previously told you a book lying on the table. So here is a book lying on the table. So two forces are acting on it. Gravitational force, which is the action, and the normal force, which is the reaction. So in this case, action and reaction both are equal. So that's why net force is 0. And body is also not rotating. So this is the example of static equilibrium. Second example is beam balance. In beam balance, you see we are taking two bodies at two different positions, two different corners, but both body has same mass. M1 is equal to M2. So in this case, gravitational force or the weight of the body will be equal. And the distance is also same. Suppose this is d, this is also d. So moment of force with respect to this body is which one direction? It is anti-clockwise direction. So anti-clockwise direction is positive and this is going clockwise direction. So it is negative. So in this case, we know that moment of force for the clockwise is positive. So we can say that m1g into d, which is positive sign, plus minus m2g into d. So plus and minus will be cancelled. So net moment of force is 0. So in this case, no rotation takes place. Now we'll see the dynamic equilibrium. When a body remains in the state of motion under the influence of several forces, the body is said to be dynamic. Means here the state of motion takes place and in the static, a state of rest takes place. So let's take one example here, raindrop. So see, rain wants to go down because of the gravitational force. So here gravitational force is acting. We know that when the drop is going down, that time air resistance is present. So air resistance will not allow this water droplet to go down. So it will apply in the upward direction and the gravitational force is acting downward direction. So both will cancel it out. So the raindrop will move with the uniform motion. Let's take another example. This is example for uniform circular motion. So we know that uniform circular motion, the speed is constant, but the velocity changes. So here speed is constant means it is a case of dynamic equilibrium. Now we'll study our next topic, principle of moment. This topic is very important with respect to numerical point of view. Definitely 3 to 4 mark question comes based on this principle. So what this principle says, if the algebraic sum of moment of all the forces acting on the body about the axis of rotation is 0, then the body is in the equilibrium. As I told you previously, when the net moment of force is equal to 0, then the body is in the rotational equilibrium, means the body is not rotating. So this principle is called as principle of moment. But how we'll use this principle for solving the problems? So before that, we see the formula of the principle of moment. So according to the principle of moment, sum of the anti-clockwise moment is equal to the sum of clockwise moment. So if you add all the clockwise moment and all the anti-clockwise moment separately, you add both and if they are equal, then the body is at the equilibrium. As you see this example here, this is a rod and this is a pivoted point O or it is a fulcrum. So I am applying two forces F1 and F2 at the two ends of the rod, end A and end B. So we always consider the distance of the point A from the fixed body, which is the O. So OA is equal to D1 and OB is equal to D2. So you see this force F1, which direction it is rotating? It is rotating in the clockwise direction. We always consider with respect to the fulcrum. So fulcrum is in this direction, so we make like this. So it is rotating anti-clockwise direction. So in this case, it is positive. Here you see F2, where it is going clockwise direction. So it is negative. So moment of force based on OA is the F1 into D1 and the moment of force is F2 into D2. Anti-clockwise moment will be F1 into D1. It is equal to F2 into D2, because F2 into D2 is clockwise, F1 into D1 is anti-clockwise. If you have two or more than two forces, so you have to do the same way. You have to write the clockwise and anti-clockwise values. I will explain you few examples based on this topic. Let's start with the first question. As you see in this question, figure shows two forces, each of the magnitude 10 Newton, acting at the point A and B at a separation of 50 centimeter in opposite direction. So you see this figure. Here in this figure, we are applying two forces of same magnitude 10 Newton, 10 Newton at a distance of 50 centimeter. And this is the fixed point O. So we have to calculate the resultant moment of the two forces about the point A, B and O, situated exactly at the middle of the two forces. Means O is situated at the middle of the two forces. So this distance is 25 centimeter and this is 25 centimeter. So let's solve it. So for resultant, if we consider at point A, so this force which is acting at point A, in this case moment of force will be 0. Why it is 0? Because in this case D value is 0. There is no D present or there is no R present. Means the force is acting on the point A. So in this case torque will be 0. Moment of force will be 0. So at A we have 3 points we have to consider. Moment of force at A, and then moment of force at OA, and then moment of force at AB. So see, moment of force at A is 0. Why it is 0? Because D is 0. Moment of force OA. OA is, this is your OA. Okay. So in this case, no force is acting at O. So F is 0. So from there, we can say that moment of force is also 0. Why? Because F is 0 at O. What about the moment of force at AB? So at AB, this is the distance, which is 50 centimeter. We can write it as 0.5 meter. And force is 10 Newton. So we can write it as 0.5 into 10. So it is total is 5 Newton meter. So this is the answer for the point A. Similarly, at point B, the force is acting at the same point B. So in this case, D is 0. So we can write it as resultant moment at B is torque at B, torque at OB, and torque at BA. So torque at B is 0 because D is here 0. OB. OB means we know that there is no force acting at O. So torque is 0 because F is 0 at O. Third is B into A. So same as A, B distance with respect to A is 0.5 meter and the force is 10 Newton. So this is 0.5 into 10, it is equal to 5 Newton meter. But one thing we have to note it down, direction. As moment of force is a vector quantity, so for A and B we can also check the direction. So with respect to A, force is acting downward direction, so it is a example of clockwise. So that's why this is negative, or you can simply write 5 Newton meter with a clockwise. Similarly, for the B, this is the point B here, and here is the force, it goes up. So it will also follow the clockwise. So it is also negative. So that's why here you can put negative or 5 Newton meter clockwise. Now we'll see for the point O. This distance is 0.25 meter because it is the middle of AB and this is also 0.25 meter, and one force is upward and another force is downward. So it is an example of couple. So directly we can use the couple formula. So at O, total resultant is F into D. This is the couple formula. So 10 into 0.5, it is 5 Newton meter. And the direction is, because it is going upward direction, so it is a minus, or 5 Newton meter clockwise. Now we'll see next question. In this question, a uniform meter rod balances horizontally on a knife edge placed at 58 centimeter mark when a weight of 20 gf is suspended from one end. Draw the diagram of the arrangement and what is the weight of the rule. So let's make the diagram first. As you see, this is the diagram of the arrangement. In this, we are taking a uniform meter rod. So uniform meter rod means 1 meter rod or rule. So here it is equal to 100 centimeter. So according to the question, fulcrum is present at the 58 centimeter mark. So this is the fulcrum and it is present 58 centimeter mark from one of the end. This is the end. So other end will be 42 centimeter. Now the weight of the rule is present at the 50 centimeter mark because the weight of the body is concentrated at the center. So this is 50 centimeter. So because of the weight, the body wants to move down, the rule wants to go down. So to balance it, we will apply a 20 gf force on the other end. If we apply on this end, so both the weight will be on the same side, so it will definitely go down. But here we have to balance the rule. So that's why the 20 gf is present on the other end, which is the point B. So now it is a case of a equilibrium. So we will use the principle of moment of force. So we know that moment of force on the clockwise direction is equal to the moment of force on the anti-clockwise direction. So this weight is following which direction? Anti-clockwise direction. And this 20 gf is following clockwise direction. It means that weight is the anti-clockwise direction. So we can write it as W, and its distance from the fulcrum is 8 centimeter. We always consider with the fulcrum. So 8 into W is equal to 20 gf. And what is the distance from the fulcrum? 42 centimeter. So W is equal to 20 into 42 divided by 8. 4, 21, and this is 5. So 105 gf. So total weight of the ruler is required 105 gf. Then the body is at the balance phase. This is the answer. In this question, figure shows a uniform meter rod placed on a fulcrum at its midpoint O. Here is the midpoint O, this is the fulcrum, and having a weight 40 gf at the 10 centimeter mark and a weight of 20 gf as 90 centimeter mark. So this is 40 gf which is present at 10 centimeter mark from the origin, and 20 gf is present as 90 centimeter mark from the origin. Is the meter rule is equilibrium? If not, how will the rule turn? Means they ask, first identify whether it is in the equilibrium or not. If it is not in the equilibrium, how we can find which direction it is rotating? So see, we know that moment of force, first let's make it this point as A, this is already O, and this is B. So moment of force for AO is equal to 40 GF. What is the difference? We notice it here, 40 centimeter. This is 40 centimeter. So we can write it as 40 GF into 40 centimeter. What is the moment of force for BO? 20 GF into the distance is here 40 centimeter into 40 centimeter. So it is coming as 1600 GF centimeter, and this is 800 GF centimeter. Direction, if we check, 40 GF will form anti-clockwise and 20 GF will form clockwise. So it is negative and this is positive. So here OB will be negative. So it means that net moment of force is not equal to 0. So it is not in the equilibrium. So in the first part, we can say that no, it is not in the equilibrium. Second, how will the rule done? So see, moment of force 1600 GF centimeter minus 800 GF centimeter. So it is coming plus 800 GF centimeter. So plus represents anti-clockwise direction. It means that the meter rule will move in the anti-clockwise direction. In the second part, they are saying that how can the rule be brought in equilibrium by using an additional 40 GF of the weight. Means 40 GF of the additional weight is now given. So how we will make the body to the equilibrium? So we know that moment of force is 800 GF centimeter and we have to substitute the mass of 40 GF. So for this we can say that 40 GF into X. Let's assume that 40 GF is present somewhere in the right side and its distance is X from the fulcrum. So it is equal to 800. So X is equal to 800 by 40, 20 centimeter. So when we place the object at 20 centimeter from the fulcrum, so then the body will be the equilibrium state. And from the 0, it is 70 centimeter. Now we will study about the center of gravity. So in center of gravity, first I will explain you one example so you get idea what is center of gravity. As you see in this figure, I am taking any random body and inside a body there is infinite particles present. But for better understanding, I took three particles as a reference. Particle 1, particle 2 and particle 3. So we know that if we have any particle, it must have a mass. And when this mass is present inside the gravity, so it must be gravitational force acting on it. So the gravitational force acting on a particle is called as weight. So for the first particle, weight is W1, second W2 and third is W3. So if we assume a point Z, with respect to this point, the distance of particle 1 is r1, the distance of particle 2 is r2, and the distance of particle 3 is r3. If we have to find the moment of force with respect to g and 1, so we can write it as it is equal to w1 into r1. R1 is the distance and the W1 is the force. Similarly, G2, W2 and R2, G3, W3, R3. So here we are not focusing about clockwise or anti-clockwise direction, but we know that when it is a clockwise, then it is a negative moment of force. And when it is a anti-clockwise, it is a positive moment of force. So when we add all the moment of forces and at a specific point, if we are getting it as 0, then that point is consider it as a center of gravity. So in this case, point Z is consider it as a center of gravity because at that point total moment is 0. So for each and every body, there must be a one point where net moment of force is zero. For a symmetric body, generally it is the geometrical center. But for non-symmetric body, it could vary. So first we note down the definition of center of gravity. Center of gravity of a body is the point about which the algebraic sum of moment of weights of all the particles constituting the body is zero. Means net moment of force is zero. So few points we have to always remember in term of center of gravity. First is the position of the center of gravity of a body of given mass depends upon its shape. Means different shape has different center of gravity. If we take a rod and if we take a ring, both has same mass, but their center of gravity is changing. For the rod, it is the midpoint, and for the ring, it is the geometric center. Second point, it is not necessary that the center of gravity always be within the material of a body. Like previous example where we took a rod. So in this example, center of gravity is inside the material. But if you take a ring, center of gravity is not present inside the ring. It is outside the ring. So it means that at this point, total moment of force is zero. Next is, by the concept of center of gravity, a body of weight W can be considered as a point particle of weight W at its center of gravity. Means at center of gravity, we consider the body as a point particle, and there all the forces we represent. Suppose if we have a body, this is the body and this is the center. So all the forces we represent with respect to the center of gravity. You might also notice in the diagram, forces are present at the center of gravity. Now I will explain you some examples based on center of gravity. First is uniform rod. So in uniform rod, center of gravity is the midpoint of the rod. It is a uniform rod. If it is a non-uniform, then it will vary. If you take a rod where the mass is changing like this way, is not at the center, shift to the other place. Circular disc. Circular disc center of gravity is at geometric center. Hollow cone. So in hollow cone, center of gravity is h by 3. If this is the total height h, so it will lie h by 3. This is h by 3. Means it will lie below the center or below the midpoint of the height. Here is the h by 2. So it will move downward direction or towards the base. So this is a table which you have to remember, and generally 1 or 2 mark question directly comes from this table. They ask like what is the center of gravity of hollow cone, solid cone, circular ring in MCQs, and you have to remember the position of the center of gravity. Now we will move to the last topic, which is uniform circular motion. So in uniform circular motion, first we will know what is circular motion. Circular motion is the motion of an object along the circumference. You see the running track. So athlete, they are running along the circumference. So it is a circular path. And when the motion happens in this circular path, is called as circular motion. So circular motions are of two types: uniform circular motion and non-uniform circular motion. So first we start with uniform circular motion. Uniform circular motion is a type of circular motion in which speed is constant. Velocity will change because direction is changing, but speed will be the same. Let's understand this point. This is a uniform circular motion. It means that speed is constant each and every point. Same speed at A, B, and C. But you notice when the body moves from A to B, its direction is changing. Initially it was going upward direction. Now it start moving on the left direction. Again at C, it moves downward direction. So each and every point direction is changing. So we know that velocity is of vector quantity. So it means that it has both magnitude as well as direction. So here speed is constant, so magnitude is same. but direction changing. And when this direction is changing, so the velocity will change. And when the velocity is changed, so acceleration is formed because rate of change of velocity is the acceleration, means A is equal to V by T. So it means that when circular motion takes place, so it means that circular motion is considered it as a accelerated motion because acceleration is present. I hope you understood this part completely. Non-uniform circular motion. So non-uniform circular motion means variable speed when the speed is not same. But in uniform circular motion, speed was constant. So definitely here speed is also changing. Velocity will definitely change and acceleration is formed. So both the uniform circular motion and non-uniform circular motion is the example of accelerated motion. Next is difference between uniform circular motion and uniform linear motion. So in a uniform linear motion, you studied in the ninth grade that when a body moves in a straight path with a constant speed, so then it is said to be uniform linear motion. So see, in this case, direction of the body is not changing. It's a straight path and the body is moving the straight path. So in this case, speed and velocity both are constant. So when speed and velocity both are constant, it means that there is no acceleration present. So acceleration is zero. But in uniform circular motion, speed is constant, but velocity changes. So acceleration will be formed. So we can note down the definition. In uniform circular motion, the speed and velocity both are constant and acceleration is zero. But in uniform circular motion, the velocity is variable, speed is constant, and it is accelerated motion. In uniform circular motion, we focused on speed, velocity, and acceleration. But we know that when acceleration is present, it means that there must be the force acting on it. Because of the force, acceleration is produced. So in uniform circular motion, there are two types of forces. One is the centripetal force, another is centrifugal force. So let's start this topic. So in centripetal and centrifugal force, I will first explain with a simple example what is the difference between centripetal and centrifugal force. So here you see this is a figure where here is a car and inside the car two person A and B is present and the car moves with a speed of v and one person which is outside the car, it means that it is present on the ground. So according to the person A and B which is inside the car, they are at rest. So what they will notice that actually we are at rest but C is moving towards the left because car is moving towards the right. But with respect to person C, car is actually moving on the rightward direction. So here two scenario we noticed. One a person on the ground and another the person inside the car. So according to person C, the car is moving towards right, but according to the person A and B, they are at rest, but person C is moving towards the left. So because of these two different approach, our force also changing. One is the centripetal and another is the centrifugal. So centripetal force is the actual force that we analyze with respect to the ground. But if a force which is analyzed by a person which is inside a body and the body is moving, so then it is a centripetal force. Both centripetal and centrifugal force are acting on the circular motion. So this was example of linear motion, but my motive to explain this example to just give you idea how the approach of viewing changes the approach of force. Let's take another example. In this example, here is a earth and here is a sun. So we know that earth revolves around the sun and the speed of this earth rotation is constant. It means it is example of uniform circular motion. So when our reference is sun, So with respect to that, Earth is rotating. But suppose a person is present on the Earth. In the morning, the position of the sun is different, and in the evening, the position of the sun is different. It means that sun is moving, I am at rest. So as the previous example, again two different references are here. One with respect to sun and another with respect to the person lies on the earth. And both the reference has different approach. So now let's start with the centripetal force. Here, initially, a body moves with a constant speed of v. But we apply a force F. Here you see, we apply the force F on this body. So by applying the force, the direction of the body starts moving. Initially, the body was at A and we apply the force. So its direction now starts changing and it reaches to the point B. So this force is always perpendicular to the direction of the speed. Here in this case, speed is on the x-axis. So force is perpendicular, so it is on the y-axis. So each and every point A, B, C, D, E and F, direction is continuously changing and the force is perpendicular to the direction of motion. So you notice that it forms a circular path. This is the one thing we noticed. Second thing, if you extend all the forces will meet at the center of the circle and its direction is towards the center. So when the force is acting on a body and it forms a circular motion, so the force is said to be centripetal force and its direction is towards the center. So let's note down the definition. Centripetal force is the force acting on a body moving in a circular path in a direction towards the center of a circular path. So centripetal force always acting towards the center. And this centripetal force is a real force because it exists when we consider our reference on the ground. But as I told you, we have second reference where we consider the body is present in the moving object. So then centripetal force will not present and centrifugal force is formed. So centrifugal force is a pseudo force or a fictitious force because we are not considering with respect to the ground. We are considering with respect to the moving body. Centrifugal force is the force assumed by an observer moving with the body to be acting on the body in the direction away from the center of circular path. Let's understand with example. As you see, this is a circular motion. Here we consider a box. Inside the box, one person is present. So let's make a connecting rod. So when the circular motion takes place and our reference is the person present inside the box, so the person will feel the force is acting away from the center. Means the person starts moving away, like in this case here, because our reference is person. So that's why this force is called as centrifugal force because we are referring an observer moving with the body. So centrifugal force is a fictitious force or the pseudo force. Let's take one example. In this figure, I'm explaining you what will happen if there is no centrifugal force. What will happen if there is no centripetal force acting on the body? So you see, we are taking a string where the tension is present and on the string a stone is present and the stone is forming a circular motion. So suppose if we break this string, so then we will notice that the body or the stone starts moving tangentially away from the circular path and it will move with the constant speed. So here speed is not changing. So it is a reverse of our previous example where I explain you when the initially the body was moving with a speed of v and we apply the force, so it start forming a circular path and it is a circular motion. And here reverse happen. When we break the string, so again it moves to the initial position. And here we are assuming no external force is acting on the whole system. So then it will move with the uniform motion. So I covered all the topics of this chapter force. If you like this video, definitely subscribe it, share it, and if you face any problem in this topic, you will also comment me in the comment section. Thank you.